Well, welcome to the module from Honors Secondary 2 titled Working with Complex Numbers. This should be in addition to the work that you've done in your regular Secondary 2 class where complex numbers were introduced. We're going to extend that idea to include division of complex numbers and also introduce an idea called the modulus. It helps us with representing vectors and connecting complex numbers to vectors. Here are the things we'll learn about. First, we want to take a minute to review what you've already learned about complex numbers. Then we'll define a term called the conjugate of a complex numbers. That allows us to do division. We've already done addition, subtraction, and multiplication. Now, with the conjugate, we'll be able to also do division of complex numbers. Third, we'll define what's called the modulus of a complex number and understand how that relates to vector representation of complex numbers. And we'll even define something called the complex plane. That's a way of representing a complex numbers with an ordered pair, similar to an XY coordinate system. By extending the number system to include complex numbers, this allows us to represent all the solutions to an equation, both real solutions and imaginary solutions. And believe it or not, imaginary solutions can sometimes help us describe real situations in our world. Now remember, in the honors modules, you should first watch the video, take notes as you go through. After you've watched the video and recorded your notes, then you'll want to go on to what we call the guided practice. These are available on your website. You'll work through each of these practice problems and then check your answers. They're all given to you there. After you've completed the guided practice, you're ready to start your own individual assignment for this module. All of these tools are available to you on the website for Secondary 2 Honors. In reviewing what you've already learned about complex numbers, one of the things we want to talk about is the representation. We typically write complex numbers in this form, a plus bi. We call a the real part of the number. Bi then represents the imaginary part of the number. We say it's the imaginary part because we previously defined the value I to be the square root of -1. And you know there is no number that multiplies to give -1. So that's why we say it's an imaginary part. Now up to this point you've already done addition and subtraction as well as multiplication of complex numbers. Let's look at some examples. For instance, the complex number 2 plus 3i might be added to the complex number -4 minus 5i. Well, addition is as simple as you would think. We simply combine the real parts of the number and then we separately combine the imaginary parts of the number. So in this case our solution would be -2, that's the real part, and then combining the imaginary parts 3i and -5i, we should get -2i. We can similarly do subtraction of complex numbers. In the example here, we have the complex number -7 plus 5i, and then -2 minus I. Again, we focus individually on the real parts, and then separately the imaginary parts. Be sure to include the sign of the imaginary part. For instance here, this is a -1i. Well, we'll combine first the real parts, so we have -7 minus 2. That would be -9. Again, the -1 here in subtraction should distribute through to both parts of the second complex number. Combining then the imaginary parts, we have 5 minus a -1, or positive 6i. That's subtraction. You've also done multiplication. In multiplication, we'll use the familiar FOIL technique to multiply two binomial terms. Here's an example: 2 plus 3i multiplied by -1 minus I. The acronym FOIL helps us remember to multiply the first, the outsides, the insides, and the lasts. And that works here with binomials and complex numbers. Those are the two first terms, so our result would be -2. The outside terms multiplied would result in -2i. Remember, this number here is a -1, and we need to include it in our multiplication. Let's do the inside terms. So our result here would be -3i. And finally, the last terms multiplied produce -3i squared. Okay, well, we're ready to simplify that result. We can combine parts. Hopefully you see that these imaginary parts can be combined together, and the yellow indicates the two real number parts. Well, let's first add together the imaginary parts, -5i. That wasn't too hard. For a moment, I'm just going to rewrite -2, but then in the second imaginary part, -3i squared, I'm going to remember that I equals -1, or the square root of -1. So I squared must be the square root of -1 times the square root of -1. And that produces the value -1. Okay, a little simpler. We have -2 minus 5i plus 3. So now you see why we spoke of these two yellow pieces as being the real number parts for the number, even though initially -3i squared looked like it might be imaginary. It's really a real part. So combining these two real parts, we have 1 minus 5i as a result. Well, those are the three operations, addition, subtraction, and multiplication, that you've already done working with complex numbers. Well, the question that I hope appears to you is, well, what about division? How do I do that? In order to divide complex numbers, we need to develop the idea of what we call the conjugate of a complex number. It's really pretty simple. For instance, here, if we have a complex number a plus bi, we define the conjugate of that number to simply be the same value for a, and then change the sign of the imaginary part. So once again, this is the real part. Here we have the imaginary part. So we keep the real part just as it was before when we're creating the conjugate, but we change the sign of the imaginary part. That's what we mean by a conjugate. As an example, if we had the complex number 2 plus 3i, of course its conjugate would be value 2 minus 3i. It's that simple. Now, what good is this? Well, it helps us express division of complex numbers in a simplified format. So let's take this example. We have 2 plus 3i divided by -1 minus I. That's a division problem. In order to do division here, we're going to multiply both the numerator and denominator by the conjugate here of the denominator. So we'll do -1 plus I. Remember, we've changed the imaginary part sign and kept the real number part. We times that in the top and bottom. In essence, then, the value that we're timesing by here, since it's the same thing divided by itself, has a value of 1. We already know that multiplying by 1, the identity, doesn't change the value of the number. So its value is the same, but it will change the way it looks. We're going to use our familiar strategy of FOIL to multiply both the numerator and the denominator. Here's the result of timesing the two terms in the numerator. Negative 2 are the first two terms. Then we'll have 2i are the outside terms, negative 3i as the inside terms, and then positive 3i squared as the last terms. Let's do the same thing in the denominator. First terms multiplied give 1. The outside terms multiplied give negative I. The inside terms multiplied are positive I. And finally, the last terms multiplied are negative I squared. Okay, well that seems like a mess, but we can combine some terms together. Remember, these are the real number parts, and these are the imaginary parts. Our result here then would be negative 2 minus 1i plus 3i squared. Okay, in the denominator we'll have 1. Well, let's see. That's nice. These two terms simply cancel out. One's negative I and one's positive I. We did that on purpose. When we multiply by the conjugate, we force that middle two terms in the binomial expansion to cancel out. That's exactly why we choose to multiply by the conjugate. So all we have left in the denominator is 1 minus I squared. Recall from the previous slide that I squared is the square root of negative 1 times the square root of negative 1, or negative 1. So simplifying further, we have negative 2 minus I plus 3 times negative 1, or negative 3. In the denominator we have 1 minus a negative 1. And our simplest form would be negative 5 minus I over 2. Now, we traditionally try to rewrite a complex number separating the real part from the imaginary part. So let's split this fraction up as negative 5 halves minus 1 half I. That's the division or quotient of 2 plus 3i divided by negative 1 minus I. Again, we have a real part and we have an imaginary part as the result of the division. That's how we divide complex numbers. Well, let's work through one more example where we find the conjugate and actually use it in a division here. Okay, well let's take the complex number 4 minus 2i and divide it by 3 plus 5i. Again, the key is to find the conjugate of the denominator. So 3 minus 5i, and we multiply that in both the numerator and the denominator. Using the FOIL process, we get this result. 12 minus 20i minus 6i plus 10i squared. Okay, let's move to the denominator. 9 minus 15i plus 15i. Here again are the two middle terms. The imaginary parts will cancel out. And finally, the last produces negative 25i squared. Okay, well we know already that I squared is negative 1. So we'll simplify this to become 12 minus 26i minus 10, and in the denominator 9, these terms subtract away, and we have plus 25. That's the negative 25 times the negative 1. Okay, our simplest form would then be 2 minus 26i divided by 9 plus 25, that's 34. We'll want to split this up, so we get then 2 over 34 minus 26 over 34i. And since these fractions can be simplified, we'll write 1 over 17 minus 13 over 17i. That's the division of these two complex numbers here. Now, we can do division of complex numbers as well as addition, subtraction, and multiplication using our calculator. In using the TI Inspire to work with complex numbers, we first should set up the settings for complex numbers. We can do that by going to the home screen here. That's the little icon with the house. Then we'll choose this option number 5 for settings. We like to set up our document settings, and you can see in real and complex. Let's represent these numbers here in rectangular format and choose OK. Okay, let's just go to the calculator screen and we'll enter some division. We're going to do the problem that we previously did here, 4 minus 2i divided by 3 plus 5i. I'll choose here the option for fractions and enter the number 4 minus 2i. 4 minus and then 2i. The value I comes from the list here where we see the pad for pi. There's the value I. And then by just pushing the tab button, we move to the denominator, and that's 3 plus 5i. And again, we grab the value for I. And we press enter, and that should give us the result, the division of the complex numbers. Now, if we compare the answers here with what we got, 1/17 minus 13/17i, they're exactly the same. Now you can do addition, subtraction, and multiplication in the same way using your calculator. It works similarly on the TI-83 or 84 calculators as well. We should be able to do all of those operations by hand and with the calculator. We now want to define what we call the modulus of a complex number. We define the modulus in a very particular way. It's the square root of the sum of the squares of the real part and the imaginary parts of the number. So for any complex number a plus bi, we've said again that a is the real part and b is the imaginary part. We're simply going to square both of those parts and add them together and take their square root. Let's go through an example of finding the modulus. In this case, we'll use 2 plus 3i. The modulus then would be the square root of the real number part, 2 squared, plus the imaginary part squared. Now we don't include the I, just the b part, so 3 squared. So we have then the square root of 4 plus 9, or the square root of 13. That's what we mean by a modulus. Let's go through another example here. Let's take the imaginary number, or the complex number, -5 minus I. Its modulus, just as we've done before, is the square root of the real number part squared plus the square of the imaginary part, coefficient, -1 squared. So we'll have the square root of 25 plus 1, or the square root of 26. You can see that the modulus is a real number. It never has an imaginary part to it at all. In this case, they're radical expressions, square root of 13 and the square root of 26, but they have no imaginary part. Okay, well, what good is this modulus thing? Well, let's try to show a vector format for a complex number. In the previous example, we worked with the complex number 2 plus 3i. Remember, this represents again the real part, and here's the imaginary part. Just as we can represent the ordered pair 2, 3 on a coordinate axis system, we can represent a complex number on a coordinate axis system. We will let the x value be what we call the real part of the number, and the y-axis will represent the imaginary part. So 2 plus 3i is really just like plotting the point 2, 3. 2 is the real part, and 3 the imaginary part. That represents the number 2 plus 3i in what we call a complex plane. Well, what's the modulus got to do with it? Well, remember we calculated the modulus to be the square root of the sum of the real part and the imaginary parts squared. So we got the square root of 13. What that is, as you can see from the Pythagorean theorem, is simply the length of this number from the origin. We use the Pythagorean theorem, 3 being the imaginary length and 2 the real number, to get the length here, square root of 13. You should recall from your honors portion of secondary 1 class that represents what we call the length of a vector, whose beginning is at the origin and end is at the point 2, 3. That's what we mean by a modulus. Let's try a second example. We had previously used the complex number -5 minus I, and we calculated its modulus. It was the square root of -5 squared plus -1 squared, and we got the square root of 26. Well, that number plotted in the complex plane would be -5, -1, right here. Again, the values here come from the real part and the imaginary part of the number. So we go 5 to the left and down 1. That's the imaginary or the complex number, -5 minus I. The modulus then represents the length from the origin to that point. We can see that the Pythagorean theorem is used. 1 is the length of the side here, or -1, and 5 the length here. So we do -5 squared plus -1 squared produces the modulus, which we call the square root of 26. Again, that represents the length of the vector here at the position -5, -1. Well, that's it for our exploration or extension of the complex number system. In next year, when you work in Secondary Math 3, you'll use this in much more meaningful ways. We wanted to introduce how to divide numbers using the conjugate and the idea of a modulus here, and connect it to what you've previously done with vectors. Good luck as you work through your guided practice and the lesson assignment.